Welcome to section 4.3, where we will discuss the concept of mass. Our goals in this section are to be sure that we understand the difference between the concepts of mass and weight, and we also want to understand the role of mass in Newton's laws. Basically, we're going to look at mass as a resistance to a change in motion. So one way to define mass is as a property of an object that specifies how much resistance that object has to a change in its motion or its velocity. The units for mass would be the kilogram, and remember, it's one of those only SI units that has a prefix out in the front, that kilo prefix, so it's not the gram, but it's the kilogram. Now, to consider this as a resistance to a change in motion or velocity, think about something that has a lot of mass. The bigger the mass something has, the bigger the resistance it has to a change in its motion or its velocity. The smaller the mass, the easier it is to change that object's motion or velocity. Along with that, a bigger mass would now result in a smaller acceleration if you were to apply some force to it, whereas a much smaller mass could result in a larger acceleration. Think about, for example, maybe your little brother, and your little brother is on a bicycle, and you give your little brother a push on his bike. When your brother's small and the bike is light, a little bit of a push would be easy to change your brother's motion. It would be easy to give him a fairly large acceleration. But if your brother grows up to become a truck driver and he's now driving a semi, and now you're standing back here trying to give him a push, your brother is bigger, the vehicle is way bigger, giving this thing a push is going to result in a very, very small acceleration, if any, and a much, much larger resistance to a change in its motion. Another way to think about mass is as that inherent property that is independent of an object's surroundings and your method to measure it. Basically what we're saying is that it doesn't matter where you are. Mass is inherent to the object and it will always be the same value. So when we think about mass versus weight, they are two different things. The difference is that with mass, that mass is the same anywhere you go. If you are a 60 kilogram person, your mass will be 60 kilograms on Earth, 60 kilograms on the moon, and 60 kilograms in deep space. But when we look at weight, weight is more of a force that a planet or something pulls on an object with. And so that force would change depending on gravity, depending on that force or that pull. So your weight would be much different on Earth versus the moon versus deep space. So mass is a scalar quantity, which means you have those normal arithmetic rules that go along with it. You could just add, subtract, without having to deal with any sort of vectors or direction that would go along with it. As we continue to analyze mass, we can describe it quantitatively by comparing accelerations that might result from a given force. Let's go back to the example of your brother on a bike versus your brother on maybe a semi. If we were to look at this equation here, we'd see that from a given force, the accelerations would be an inverse ratio or relationship to the masses. Here's what we mean by this. If we were to say that M1 was maybe your brother on the bike, this would be the small mass. It's not very big. The kind of acceleration that would now result from that would also be a much larger acceleration. Small masses, if you give them a push, are going to result in very big accelerations. Now, if M2 was your brother while he was on the semi, this would be a much larger mass, and it's going to have a much bigger resistance to a change in its motion. So when you try to give this thing a push, it's going to have a much smaller acceleration. Now when we look at these ratios, we can see that the smaller things are on the top of the ratio and the bigger things are on the bottom of the ratio. Essentially what we're saying is that you can compare masses and accelerations, and when you do, you end up with this inverse relationship of mass to acceleration. The smaller the mass, the bigger the acceleration. The bigger the mass, the smaller the acceleration. Now let's bring this back down here where we can look at some of our other notes. Again, we can see that on our notes here, if the mass is the larger mass, its acceleration is going to be smaller. So basically we're keeping the smaller things on one side and the larger things on the other side of these ratios. Let's look at an example of this and see how we could use this concept mathematically to solve a problem. Let's say that you have a force that's on a 3 kilogram object producing a 4 meter per second squared acceleration, and the same force is now applied to an object that is twice as big. What kind of acceleration is going to result? If we look at this as a set of ratios that can be set equal to each other, then we can take the first mass of 3 kilograms and its acceleration of 4 meters per second squared and set them up on opposite sides of the ratio. The mass of 6 kilograms would now be on the bottom, whereas its acceleration, or A2, is going to be on the top. When we cross multiply, we can set up an equation where 6 times A2 is going to be equal to 3 times 4, or 12. So when we solve for the second acceleration, we take 12 divided by 6, or get 2 meters per second squared as the resulting acceleration. This makes sense because if the object is twice as big, when the same force is applied to it, you should get an acceleration that is half as much. A bigger object is going to have more resistance to a change in its motion because of that larger mass.